Well, class, thanks for letting me be with you in this this context again. I hope that your test went well yesterday. I'm sure it did. I'm sure you studied hard, and I know that you're still being respectful and responsible. So now this video also looks a little bit different. I think I'm up in some corner, like maybe up there somewhere, because I was able to get my setup so that I can draw out our examples today. Should make it a little easier, certainly for me to present, hopefully for you to follow. So get your textbooks as we go to chapter 7. We're going to be doing rational expressions and their applications today. And if you would, turn your books to page 498, the fundamental property of rational expressions. And while you find that, I'll just remind you what a rational number is. A rational number is pretty much any number that can be written as a fraction. So 2/3 is a rational number. -3/4 is a rational number. 4 is a rational number because I can write it as 4/1, right? And so a rational expression is just where you have it written in a fraction form, polynomials in the denominator and or the numerator. So -6x over x to the third plus 8, or 2m cubed over 8. These are rational expressions. So the first thing we want to do dealing with rational expressions is very simple. Let's imagine we know the value, we're told the value of our variable, say x, and we want to find out what the actual numerical value is. We don't want an expression, we want to solve it, for lack of better words. So how do we do that? Well, let's just take as our expression to begin with here. Let's take as our example A, it's going to be 3x plus 6 over 2x minus 4. And for this particular example, we're told, example A, we're told that x equals 1. So then how do I solve this? All you're going to do is substitute. Since x equals 1, just rewrite it. Every you see x, just write 1. So that's going to be 3 times 1 plus 6 over 2 times 1 minus 4. And now we're just going to solve. What is 3 times 1? Is 3. You give your plus 6. And 2 times 1 is 2 minus 4. And then we just further solve that. 3 plus 6 is 9, and 2 minus 4 is -2. So the answer is going to be -9 halves. So this rational expression, 3x plus 6 over 2x minus 4, equals -9 halves when x is 1. So this is pretty simple for us. It's pretty straightforward, not hard, right? Let's do B, where we have the same, but this time let x equal 0. I'm not going to rewrite the expression because it's going to be the same expression, all 4 examples. Let's just start rewriting it. That's going to be 3 times 0 plus 6 over 2 times 0 minus 4. Okay, and then just solve. 3 times 0 is 3, and then add 6 is going to be 6. 2 times 0 is 0. Let's say 3 times 0 is 0. I'm sorry. 0 plus 6 is 6. 2 times 0 is 0. Add -4. 0 is going to be -4. And 6 over -4 should reduce to 3 over 2. And the whole thing is negative. So 3x plus 6 over 2x minus 4. When x is 0, the value is -3 halves. That's the value of the expression. Let's see. Look at example C. In this case, x is 2. And so, as you already know what we're going to do, we're just going to start substituting in 3 times 2 plus 6 over 2 times 2 minus 4. And now we're just going to solve. 3 times 2 is 6. 6 plus 2. 3 times 2 is 6. 6 plus 6 is 12. 2 times 2 is 4. 4 minus 4 is 0. And now we have a problem. 12 over 0 is undefined. Remember, we cannot divide by 0. So this expression is undefined whenever x is 2. Remember, a rational expression, go back to the top of your page here. The denominator can't be 0 because that's That's just what a rational number is. It's a fraction which denominator is not zero. So that's going to come up again in just a minute. Just know that whenever your denominator is zero, the expression is going to be undefined. We'll say a little more about that in example 2. And then finally, D, let's take x to be -2. Same exact procedure. We're going to say 3 times -2 plus 6 over 2 times -2 minus 4. And let's just solve. 3 times -2 is -6. -6 plus 6 is 0. 2 times -2 is -4. -4 minus 4 is -8. Well, is this undefined? This is not undefined because the 0 is in the numerator. Anytime you divide 0 by a number, the answer is just 0. So this is not undefined. This is allowed. This is a rational expression. It would just mean that the value of this expression when x is -2 is 0. So that's how you calculate the numerical value of an expression when the variable is supplied. You just substitute and solve, and that is example 1. So long as the denominator doesn't equal 0, you're okay. If the denominator is 0, it's going to be undefined. Now, let's expand on that point just a little bit. When the denominator is, sometimes you want to know when a denominator is going to be 0. You want to know when an expression is undefined. We'll talk about asymptotes later on. That's what that has to do with. I'll say something about in just a moment. So let's look at example 2 and look at A. So suppose I have x plus 5 is my expression, and it's 3x plus 2. And I'm not given an x. I want to know at what value of x does this expression become undefined? What value is that? In other words, at what value does the denominator equal 0? Well, I'm just going to set that to be 0. I can ignore x plus 5. 3x plus 2 equals 0. And then we just solve that. So if I were to do 3x plus 2 equals 0, well, I can just subtract 2 from both sides. That gives me 3x equals -2. Divide by 3 so that x equals -2/3. If x is -2/3, then I know that the entire expression is undefined. So when you're finding out what's an undefined expression, just take the denominator, set it to equal 0, and then solve that equation. Let's look at example B to see one that's just a hair more complicated. 9m squared over m squared minus 5m plus 6. Okay. Now, at what value does this expression become undefined? I'm just going to set it to equal 0. And now you recognize this is a trinomial. This is a standard quadratic equation set to be 0. And we're just going to factor out this. And we know that we have some factors of 6 that give us -5. And that's going to be 2, -2, and -3, because -2 times -3 is 6, and -2 plus -3 is -5. So we're going to set m minus 3 and m minus 2. Both of those equal 0. I'm not going to write them individually. I could. M minus 3 equals 0 would give me m equals +3 because you add 3 to both sides. And then for this one would be m equals +2. So my two values are 2 and 3. If I put 2 and 3 back into this equation, it's going to equal 0. And I'll encourage you, try it real quick. 2 squared minus 5 times 2 plus 6 is in fact 0. And 3 squared minus 5 times 3 plus 6 is in fact 0. Give it a try, and you'll find out it is in fact undefined. I'm not going to write out C because there's nothing, it's just to say it's based on the paper, but just look. 2r, r squared over plus 1. At what value is this undefined? This one is never undefined. And the reason it's never undefined is because r squared will always give you a positive number unless it's 0, because 0 squared is 0, but even then plus 1. And so there's no way to get r squared to -1, because taking into imaginary numbers, a square is always going to be a square is always going to be a positive number. So if you don't see that r squared plus 1 is always going to give you a positive number on bottom, then just play with it until you realize, if you think you can get r squared to get -1, let me know how that goes. All right. So now we know how to set example 2. Now we know how to discover the value that makes it undefined. Last thing I want to look at example 3a. We're only doing 3a. Tomorrow we'll do 3b and on. Now we just want to write our rational expressions in lowest terms. In other words, we just want to reduce the rational expression. So the idea here is if you have any polynomials, pk over qk, you can just cross out those k's. And we've been doing this for a long time. Of course I can cross it. This equals p over q. We're going to do this step by step and show you why. And we're going to start with a very simple example and make it more complicated than it needs to be. So suppose I have 30 over 72. Now, you've been doing this for a long time. If I wanted to reduce 30 over 72, well, I know both of those are divisible by 6, right? So 30 divided by 6 is going to be 5, isn't it? Yep. And 72 divided by 6 is 12, and we're done. Now, that works with a simple number like this, but we want to make sure we know the underlying reasons so we can do more of it later on. So let's kind of ignore this. Let's do the long way. Whenever the way you actually write a rational expression with polynomials in lowest terms rather than just reducing is I want to actually factor out this as far as it goes. So what are the factors of 30? Let's do a factor tree. Well, ignoring 1 and 30. Well, 2 will go into it, and 2 times 30, 2 will go into 30. That's 15, and I can factor 15 out into 3 and 5. That's all my factors. And 72, we can do the same. Gives me 2 and 36, and 36 becomes 2 and 18, and 18 is going to be 2 and 9, and 9 becomes 3 and 3. So in other words, my numerator is 2 times 3 times 5. You see, that's these 3 guys right here for the numerator. And the denominator, I'm going to take all these here, which is 2 times 2 times 2 times 3 times 3. Oop, I'm off my screen. Y'all were yelling at the camera screen right now. I can't see it, Mr. Morrison. All right, so you see? So I've taken the numerator and factored all the way out, and the denominator, and I've factored all the way out, right? And now notice I have 2 times 3 and 2 times 3. See that? So that I could theoretically, I could rewrite this as 5 times 2 times 3 over 2 times 2 times 3 times 2 times 3. And since these are the same, I can cross those out. They just, as you know, number of equals 0. And now that's 5. What's 2 times 2 is 4. 4 times 3 is 12. So that becomes 5 over 12, which is the same thing we saw a minute ago. Okay. That's a long drawn out process for just reducing. You've been doing this since what? The 3rd grade or earlier than that, reducing things. But it's going to be important starting tomorrow that we know how to expand out the process to reduce it. All you're doing is factoring the numerator as far as you can, and then factoring the denominator as far out as you can, listing out the common factors, and then crossing them out because they are equal to 1, and then you're good to go. So all we did today, quick summary, 30-second summary, is we figured out how to evaluate if we were given what the value of x is, how do we evaluate, how do we find the numerical value of an expression? Second, we learned how to find at what value the expression is undefined. We set the denominator to 0. This is something, believe it or not, you will use later on in math. There are these really cool shapes called asymptotes that you're going to make a great deal of use out of, certainly in Algebra 2. They're used a lot. They're these there are these circles, this, just so you know. You've seen a lot of lines that look like this. Well, an asymptote looks like this. So they're lines that they curve up and they never get to some value. And so sometimes it's useful to know at what value it stops and you can never get there. You can put more and more and it'll just never get there. So those so there are all these asymptotes. So that is what you're looking at with asymptotes. That will come up later on. And then we learned just, again, how to factor out this into more detail. So with that, we're going to be done. What I'm going to want you to do is down here, we get over to page 7.7.1 exercises. I believe I assigned 8 through 30 even, since we did 3.1, 8 through 30 your evens, all right? And with that, I'll write at the top just for 8 through 30 evens. If that's not the lesson plan, let me know, but I think that's what I'll list it. All right, with that, we're done. Y'all have a great one. I'll see you again tomorrow. God bless.